Hi everyone and welcome back. I'm here Alfonso Mendez, and in this video we will see how to add penalties and constraints in the RBF regression available in the open source code Spicy. This is the second of the 5 videos in the mini course that we have prepared for the theoretical background of our code Spicy. Now, in the first video we saw two kind of problems that can be tackled in Spicy, and we saw that we were looking for minimizing a loss function. Now, to add penalties and constraints, we can add terms to our cost function to obtain the so-called augmented loss function. The first kind of terms that we will add are related to penalties, and the second are related to constraints. Both kinds of terms are functions of the weights, but the main difference is that penalties are going to be multiplied by scalars that we can predefine, whereas constraints would be multiplied by vectors of Lagrange multipliers that will depend on the problem. This means that we can fix the alpha, we will fix the alphas during our training, but we will have to solve for the lambdas. Now, the minimum of our augmented loss function will be obtained when the gradient with respect to both the weights and the Lagrange multipliers is equal to 0. Here are some examples of penalties and constraints that we will be adding. As we will see in a minute, all penalties will be quadratic. The one that we will use the most, basically in all problems, is on the L2 norm of the weight vectors. This is also known as Tikhonov regularization. On the other hand, all the constraints that we'll consider are linear. Keep this in mind, we will always use quadratic penalties and linear constraints. Linear constraints can be, for instance, the fact that the value of our predictions at certain points has to be equal to a certain value. So we will take the residuals of this equality as a constraint. This is what we will call Dirichlet condition or Dirichlet constraints. Or we can impose that derivatives of our approximation along a certain direction, say along the normal direction of a boundary, has to be equal to a certain value. So when we take the residual of this equality and we set it equal to 0, we obtain what we call the Neumann constraint or Neumann condition. Note that we call this Dirichlet and Neumann constraints because we will use them to put these kind of boundary conditions, but in fact the location at which we are going to put these constraints need not to be restricted on the boundaries. They can be placed anywhere in our domain. Now, why do we want to have only quadratic penalties and linear constraints? Well, because in this specific case, when we set the gradient of our augmented loss function to 0, we obtain a linear problem. This is, for example, the linear problem that we obtain if we consider 2 penalties and 1 constraint. So here note that the penalty has the first term being the classic Tikhonov regularization term, and the second being a sort of weighted norm of the weights. Alpha 1 and alpha 2 defines the relative importance of these two, and once again this will be set by us. As a linear constraint, we take a general operator CH, so that CH times W has to be equal to small ch, and so the difference between them sets the residuals. Now, no matter how many quadratic penalties and linear constraints you introduce, you will always end up with a linear system that has the same structure, and that looks like this. The system matrix is made of 4 blocks with matrices A and B. The vector of unknown has weights and Lagrange multipliers stacked into a single vector, and we have some vectors on the right hand side. Now, the block matrix A contains all the terms linked to W in the augmented loss function. For the example which we are considering, it looks like that. The first term comes from the prediction term, so the phi W. The second term here comes from the T of regularization, the T of penalty with alpha 1 importance, and the second from the weighted norm penalty with alpha 2 importance. Note that the T of term brings here the identity matrix, and this will be very important for the stability of the numerical method that we will use to solve the system. The B term collects all the linear operators in the constraint. In this case we have only one, and on the right hand side we have the projection of our known vector f, our target, on the basis phi, and below this one, below it, the value for the linear constraints. Note that we will arrive at the same, exactly the same problem for both the velocity regression and the PDE integration, the two problems which we've seen in the previous video. Of course, only as long as the differential operator in the problem of type 2 is linear, as will be the case in our problem. In the next video we will see how to use penalties and constraints for the regression of a velocity field from particle tracking velocimetry.